Hey, welcome back, folks. So now we're going to talk a little bit about learning. So in terms of our course, we've done a bunch on background and fundamentals. We looked at different models of network formation, and now we've moved towards trying to understand how network structure impacts different kinds of behaviors and so forth. We talked a bit about diffusion, and now I want to focus in a little bit on learning. And in terms of learning, we're going to basically look at two different models. We'll look briefly at Bayesian learning, and then we'll look at what's known as the de Groot model. And there's a whole variety of models out there these days, and different ways of modeling learning. And it's going to depend on who observes whom and what the network structure looks like. And there's hybrid models out there. What we're going to do is just look at these two to get some flavor of these things. And the de Groot model turns out to be a very useful one. The Bayesian one has some interesting insights and interesting questions associated with it. So we're going to start with the Bayesian learning, and we'll talk about repeated actions where people get to observe what each other are doing. So I'm deciding over time what I'm doing, and I can see what my neighbors are doing. And there's going to be an interaction between us and in terms of what I learn from what my neighbors experience and so forth. So we'll look at that a bit, and then we'll move into the de Groot model. And the de Groot model is going to be one with repeated communication where people can keep talking to each other, but there's going to be a very naive way of updating. So what I'm going to do is essentially just keep taking weighted averages of information that I get from my friends, and I'll form opinions by continuing to average things. Even though I might end up hearing from things, I might end up overweighting or underweighting. So it'll be a more naive model where I'm not fully rational in a Bayesian sense. So Bayesian learning, I mean, these people are probabilistically sophisticated. You take into account information, you update a posterior using Bayes' rule, and maximize some payoff based on that. So the de Groot model is going to be much more naive. And actually easier to work with in many ways. And there's some experimental work these days, which you can find in some of the references, which compare Bayesian models and de Groot models and other models, and find that humans are somewhat rational in what they're doing, but they have limits to their rationality, and they don't look like they're necessarily full Bayesians. And some of these naive models, alternative models, can be better at actually capturing human behavior. Okay, so let's start with the Bayesian model as a very useful benchmark and an important one to consider. And the idea here is, first of all, we can ask, will society converge? So will it be that eventually everybody converges to doing the same thing or having the same beliefs? Will people learn and aggregate information properly? So imagine that new technology comes out, and we're not sure whether this is a good technology or a bad technology, and some people start playing with it and using it, and other people can see whether others are enjoying it. Will eventually, if it's a good technology and a better one than the old one, will it take over or will it not? Will people not necessarily learn? Under what conditions might that happen? So we can ask questions about whether or not people are going to accurately aggregate information. And so I'll start with a model by Bala and Goyal from 1998. And it's a very simple setting, very natural one to analyze. So there's a number of people in some network, and we'll take this network to be a single component. So people are all going to be able to pathwise be connected to each other. So there's n players. And in this simple version of this, we'll treat it as if you have two actions, A or B. Now you can expand this to some finite number of actions. It'll be pretty obvious exactly how to do that once we get to the results. So the intuitions here are very easy to state with two actions, and I'll do a simple version of this. It's going to be obvious how to extend this beyond this. So basically, let's think of you choosing either action A or B over time, and so think of this as the old technology. A is the old technology, B is the new unknown technology, or A is acting in one manner, say keeping my money in bonds, and B is investing in some kind of stock over time. And so we've got these different actions that we can be taking over time, A or B, and A pays 1 for sure, whereas B is uncertain and it pays 2 with probability P and 0 with probability 1 minus P. Okay? And let's suppose, to make things simple, that people don't mind risk, so basically they just care about the expected value. So they know they can get 1 from choosing action A, and action B is either going to pay off 2 with probability P or 0 with probability 1 minus P. So basically B is better if P is bigger than a half. This is bigger than 1. Then they should choose B. But if P is less than a half, then they should choose A. Right? So very simple setting. B is better if P is bigger than a half. A is better if P is less than a half. But we don't know what P is. So it's a new technology. We're uncertain. Maybe we have some prior information. Maybe we have some guess at what P is, but we don't know for sure. So these individuals have to experiment a little bit with B, to find out whether P is good or bad. Okay. So they're going to be choosing actions over time. And the learning model is going to be as follows. Each period, a person makes a choice between A or B. And each period, you get a payoff. Okay, and so if I choose A, I get a payoff of 1 for sure. And if I choose B, I'm going to get a payoff of 2 with probability P and 0 with probability 1 minus P. Okay, so I try this new technology. Maybe I'm a farmer. I try a new thing, and I either get the higher payoff or the lower payoff with probability P or 1 minus P. Okay, so each period, I'm going to do that. And what does the network do? The network is such that what I also get to see is I get to see my neighbors' choices and their outcomes. Okay, so if I'm a given individual and I have 2 friends, I chose A, I got a payoff of 1. This individual chose B, they got a payoff of 0. This person chose A, they got a payoff of 1. This person over here chose B and got a payoff of 2. So basically what I learned I chose A, they chose A. I get to see that this person chose B and got a payoff of 0. This person chose B and got a payoff of 2. And every day I'm going to get all this information, and I'm going to store that information over time. And over time I'll begin to learn. So if I get, if I begin to see lots of people choosing B and lots of people getting 2s, I'm going to think, well, it's probably a good thing. P is probably pretty high. If I see lots of people choosing B and lots of people getting 0s, then I'll downgrade my belief on P, and I would be more likely to pick A. And what people are going to do in this setting is they're going to maximize their overall stream of expected payments, right? So I'm going to get $1 today if I chose A. I get some random amount if I choose B, and every day I'm making this choice, and I have an expectation of what this thing looks like, conditional on what I've seen up to a point in time. And so I'm getting some payoff. Let pi sub I at time t be the payoff I get from following a certain strategy of choosing A's and B's. And there'll be some delta less than 1, greater than 0, and I'm going to maximize that sum of discounted payments. Okay? And let's suppose that P is unknown, so I don't know it initially. It takes on some finite set of values, so maybe it could be 0.1, 0.2, 0.3, etc. Right? So it has some finite set of values, and I'm trying to guess whether B is a good thing. Okay, that's the structure. So now let's talk about some of the difficulties with this. What are the real challenges in Bayesian learning? So first of all, let's think of the following. So let's suppose that I know what the network looks like. I'm person 1, here's person 2. Person 2 is connected to some other individuals, say 3 and 4. And they're connected to 5, 6, and so forth, right? And we've been doing this for a set of periods. And what I get to see, let's suppose I'm choosing A for a while, I'm kind of pessimistic. I'm seeing that this person chose B, okay? Now, the fact that they chose B tells me 2 things. One is it tells me something about the fact that they must think B is a good outcome. But it also tells me things about what they might be seeing from other individuals, right? So over time, they've been seeing what 3 and 4 are doing, and I don't get to see what 3 and 4 did. But I know that 2 saw 3 and 4, and I know that 3 is influenced by 5, and 4 is influenced by 6, and so forth, right? So there's some network out there of a bunch of individuals. And let's suppose, for instance, just as an example. Let's suppose that I've been choosing A for a while. I see that this person is choosing B for a while. And let's suppose I see them, I see person 2 choose B, they get a payoff of 2. I see them choose B, they get a payoff of 2. B, they get a payoff of 2. So I'm thinking, wow, this is really great. And so then I switch to B, and I keep seeing them get 2s, and then suddenly I see them switch to A. What would that tell me? Well, now I have to think, well, why would they have switched to A? It's probably because their own experiences has been pretty good. It must be that they see some bad experiences somewhere else, right? So now I have to think, what are all the possible experiences they could have had? Well, it could be that they saw 3 getting bad payoffs, or 4 getting bad payoffs. Or maybe it's that they saw 3 switch from B to A. Or, so they saw both 3 and 4 switch. So I have to, in order to think about this problem, it's a very complicated problem. I have to think about what are all the scenarios that could be considered in terms of all the histories of A's and B's and what everybody is seeing, and how does that impact each person's decision, and what should they do in response to that. Okay? So the updating question here is actually fairly complicated. So I can make all kinds of indirect inferences just based on what somebody's strategy is. Okay? That's one challenge. What's a second challenge here? A second challenge is that there also could be some interaction. Let's suppose I start with a belief that P is less than a half, right? If I was alone in the world, even if I believed that P was less than a half, I know that I'm going to be around for a long time. It's still worthwhile for me to try B a few times, just to experiment, and to see if in fact maybe I'm wrong and maybe P is higher than a half. So even if I start out with a prior, it could be that I want to experiment, right? It could be that I want to try B a few times just to see what happens. And then once I've learned, that could be very valuable information, because if it pays off 2 a bunch of times in a row, I'm going to want to take B, and that's going to give me payoffs for the rest of my life. So trying something out can be very worthwhile. And so being fully rational, even if I start with P less than a half, as long as I'm making choices over time, there's an option value for trying this thing, and that's going to be positive, and I might want to try that and experiment for a while and see what happens. Okay. So now there's an experimentation that comes into play as well. Okay, well now let's suppose there's 2 of us, person 1 and person 2, right? I'd like the other person to experiment. If I think P is less than a half, why don't I let them try it, and I'll sit by and just choose A. And if they experiment and play with B for a while and it pays off well, then I can switch to B. But I don't have to pay the cost of the experimentation. I want a free ride. Okay. Now, that becomes a game which is actually going to have a fairly complicated equilibrium, especially when you start putting that game in a network with all kinds of players. And we begin to have the players connected to other players, and now we look at this simultaneous decision of who's going to choose B in this period, who's chose it in the last periods, what are our beliefs, what do I think everybody else's belief is, and so forth. So when you get to overall looking at this game, the game becomes very complicated, both because of the strategic aspects and because of the Bayesian inference. And so now you can begin to see why it might be that, in fact, when we put humans in a laboratory and ask them to play games or to make these kinds of choices, that they might not behave in a fully Bayesian manner. It's just complicated to do, and it's hard to even write the model down and solve it. Okay, so in fact, the way that let me just say a little bit about how this is solved in terms of the Bala and Goyal approach. So what they did is assume that players are not going to be strategic about this, and each person is just going to choose things which maximize their own payoff and not worry about the gaming aspect of it. And secondly, I'm not going to infer things from the fact that other people are making different kinds of choices. I'm just going to keep track of what have I seen in terms of my histories of A's and B's. Okay, so I just keep track of whatever I've seen through myself and my neighbors, and I'll just keep track of what are the relevant payoffs, and most importantly, how many times have I seen B pay off 2, how many times have I seen it pay off 0, and then I can update on what I think P is just based on those observations. And I'll ignore everything else, and I won't do the complicated updating. I won't game things. I'm just going to look at the 2's and 0's and decide whether or not I want to switch from A to B or B to A. Okay, so let's look at that. Okay, so what's a proposition you can prove then fairly directly? The first thing you can show is, let's suppose P is not exactly a half, where I'd be indifferent between choosing an action. Then with probability 1, there's a unique time, well, there'll be a time, a random time, sorry, such that all agents in a given component play just one action and play the same action from that time onward. Okay, so basically what's happening is, as long as P is not exactly a half and we would be sort of indifferent, we're basically going to eventually all end up choosing the same action, and we'll just lock in on some action and play that forever after at some time. Okay, so sometime we'll all eventually converge and play the same action forever. Okay, so that's the nature of the proposition. So let's talk through the intuition and basic proof behind this. Why is this true? And I'm just going to sort of sketch out the proof. It's fairly easy to fill in the details here. So let's suppose that this weren't true, right? So if it wasn't true, then basically somebody's going to be having to switch back and forth infinitely many times. Otherwise, we'll eventually converge. So somebody's got to be going back and forth between A and B infinitely often. And in particular, somebody, let's suppose we just have one component, and this just works, regardless of which component you're looking at. So let's suppose somebody is playing B infinitely often. Okay, so if we don't converge, somebody's got to be playing B infinitely often. Okay, now we can use the law of large numbers. So law of large numbers is going to tell us that if somebody plays B infinitely many times, then they're going to come to get an arbitrarily accurate estimate of what P is. So with the probability going to 1 in time, their belief will converge to P. And so what does that mean? Well, in order for them to keep playing B, if their belief about P is becoming arbitrarily accurate, then it must be that P is converging to bigger than a half. Otherwise, they would stop, right? So over time, they're good Bayesians. They know how accurate their belief is. They would either converge to P above half or below half, because it's not allowed to be exactly a half under our assumption. If it's above half, then they'll keep playing it. If it's below half, then eventually they would stop playing it, because now they'd be arbitrarily, accurately convinced that it's not good. So if it's not good, they should learn that, and they stop playing it. If it is good, they'll keep playing it. Okay, so it must be that if they do play it infinitely often, then it's got to be the case that they're converging to the good belief. Otherwise, they would have stopped. Okay, so now this means that they have to be converging to the true belief. With probability 1, the true P has to be bigger than a half. So then everybody who sees this person is actually going to see the sequence played. They're going to also see B played infinitely often. They're also going to have to converge to the belief that P is bigger than a half. And so they should all start playing B, right? So if this person is learning that B is good, then their neighbors are all going to have to converge. Then these people are all going to see B infinitely often and converge to P. Their neighbors are going to have to converge, and so forth. So the neighbors of agent must play B, then all agents must have to play B. So it just has to spread out. Okay? So if anybody's going to play B infinitely often, then it's got to be that it's a good thing and you learn. If not, then we've stopped and everybody had to have played A. So either somebody plays B infinitely often, in which case we converge to B, or they don't, in which case everybody's converging to A. So that gives us a proof that basically we're going to get convergence, and we're going to converge to either all playing B or all playing A. Well, does that mean that we always converge to the right action? That if P is really bigger than a half, we converge to B, and if P is really smaller than a half, then we're going to converge to A? Well, let's suppose that P is really bigger than a half. If P is bigger than a half, then B is the right thing to do. We should really be playing B. So that we will play the right thing if we actually converge to that, but it's possible that we might not converge to that. And how could that happen? That could happen if we all start pessimistically enough and we just happen to get some bad draws on B initially. So it's possible that everybody gets some bad draws on B, stops playing B, and then we never learn after that, right? So even when P is bigger than a half, it's possible for us to converge to A. On the contrary, if A is the right action, then we've got to converge to the right action, because that means that now P is less than a half. So there's no way to converge to B in that case, because if we play B long enough, we'll learn that it's not good, and then we'll all switch to A. So in a situation where A is the right thing to do, well, necessarily everyone's going to have to learn that, and we will converge to A. If B is the right thing to do, we'll eventually converge, but we could all stop playing B too soon, and we might end up just converging to B. Okay, so we will all converge to doing the same thing in this model, but whether it's the right thing or not depends on whether B is the right thing or A is the right thing. If A is the right thing, we'll definitely converge to the right answer. If B is the right thing, we might or might not, depending on what our prior distribution is and whether we get good luck in the initial draws. Okay. You could enrich this model so that you have different priors for different individuals. You can actually start specifying the priors, so what's different people's prior beliefs. And then the probability of converging to the correct action, of converging to B, for instance, when it's the right thing to do, can be made arbitrarily high. Basically, if we add many actions, as long as each action there has somebody who initially has a very high prior that action is the best one, then we'll get enough experimentation in these different actions so that we'll learn about these different actions, and society can learn arbitrarily accurately as long as there's somebody who's really willing to try out every technology. And the case where we might fail to learn is going to be a situation where nobody's convinced enough to begin with to give it a long enough try. We might end up not learning about it. Okay, conclusions. What do we end up in this model? We all end up choosing the same action, so we reach a consensus. It doesn't necessarily mean that we all end up with the same belief, because we're going to have different observations. So it might be that one of us stops with a probability. Our probabilities differ on whether B was good or not. We might end up with different beliefs, but we all believe that we're all pessimistic enough to stop. You can do speed of convergence kinds of results here. You could go through and depending on whether B is good or bad, sort of do computations. Then you have to actually explicitly solve through for these optimal actions as a function of what the histories look like. And there's a number of theorems in studies of two-armed bandits and other things in probability theory where you can get rates of convergence on these things. Laws of large numbers, especially in this kind of Bernoulli world, have well-established speeds of convergence, so you can calculate those kinds of things. And relatively, these things will happen relatively quickly in terms of the number of observations giving good information here. Limitations. Okay, so there's a number of limitations in this kind of model. One is that basically everybody was getting the same payoffs from A or B. And so when you think about new technologies in the real world, new technologies might be right for some people and not right for other people. And so when you start putting in that heterogeneity, then it's much harder for me to necessarily infer, maybe my neighbor's getting a good payoff from this, but will that be the same payoff I get? That complicates things. And that heterogeneity means that the learning might take a very different form than what it did in this model. Here we've got repeated actions over time, so everybody keeps taking all these actions and trying all these different things. There's a lot of things in which we're not trying things repeatedly over time. We're just learning about them slowly over time. So with things like global warming, we're going to get one go at it, and it's not as if we can just try infinitely often experimenting with different things, and if we get it wrong, we've got it wrong. So the repeated actions over time and getting feedback from that is a situation where we get lots of information over time and incoming information. It might be that information, we get it in slower clumps or in different bits. Here there's a very stationary environment. It could be that the environment changes, which makes things even more complicated. And finally, and probably most importantly, in this model we were not really able to take the network into account. The network really didn't play any role. All the arguments were just that somebody would eventually learn, and then the neighbors have to learn, and the neighbors of the neighbors have to learn, and so forth. So it's a simple induction argument, and we weren't able to say anything about what was going on in terms of one network versus another. Now you could do simulations and see whether speeds are faster in one versus another, but we can go to other models to try and get a better feeling for exactly how the network works on that. And that's what we'll do next when we move to the DeGroot model. That'll bring in the network very explicitly and allow us to do a lot of calculations quite easily. So that'll be our next subject. We'll start looking at the DeGroot model, where network structure is going to play a much more prominent role in the learning process.